A2 Maths, points of inflection. So as you're well aware, at different x values, as we go across here, the gradient at any of those x values varies. So for example, sometimes like here, if I look at the x value just there, you can clearly see it's going up. Whereas an x value here, which is a maximum point, has no gradient. Here, at this point, we can see that the gradient is going down, and so on. All right, so at any of our x values, the gradient changes. Now, if you have a situation where a gradient is positive, like it is here, all right, so at this point, what we can say is if the gradient is positive, that means at that point just there, this function is said to be increasing. And in fact, it's increasing there, it's increasing there, it's increasing on this side just here, because the gradient is positive. Now, if the gradient is going down though, if the gradient is negative, so in this situation, we're clearly seeing that the gradient is going downwards, same as somewhere like there, it's clearly going downwards, then the opposite is true. The function is said to be decreasing at that given point. So as the x value changes, it's either going to be an increasing function or a decreasing point on the function. But if the graph is either, the gradient is neither increasing or decreasing, then it's said to be what we call a stationary point. Now you've investigated stationary points already, so this is just an extra definition of it. If it's neither an increasing function or a decreasing function, it means it has a zero gradient, and it's what's called a stationary point. And it has a stationary point just there, it has a stationary point just here. So that's an example showing that that line there is neither going up nor down. Same there, it's not going up or down, so they are stationary points. And if the stationary point, which we've got there, is a maximum, okay, so it's a maximum, or it could be what's called, in this case, a local minimum point. Okay. But what's important to understand is if it's going from positive value to a negative value, that makes it a maximum point. Whereas if the gradient was a negative before that point and then positive afterwards, then it's a minimum. So if you can investigate what happens either side of a stationary point, you could define whether it's a maximum or a minimum. If it goes from positive to negative, it's maximum. If it goes from negative to positive, it's a minimum. Stationary points, maximum points, minimum points all should mean the same thing to you. If you see any of those words coming up in your exam, they should all mean the same thing, and that is that the gradient function equals 0. Stationary points imply that, maximum points imply that, minimum points imply that. It's not necessarily true the other way, okay? Because you might have a dy over dx is a maximum point, a minimum point, and so on. Okay, so just grab your notebooks, because this is some stuff that is new to you. If a section of a curve forms an N shape, so if you can see that clear N shape, or like the mouth of a cave, so that sort of shape just there, what you can say is that shape is what's called a concave section. So anything that can form that sort of shape is a concave section. Okay, so just make sure you've got that down in your notebook. Anything that produces the opposite, like a U shape, just there, it is a convex section. Notice it's made up of stationary points, maximum minimums, made up of all those sorts of things. It doesn't have to be though. You could just have this section here. And that's still a convex section. So a concave is that way around, like an N. Convex is the opposite to U. Okay. Right. A second derivative can show if a section is either concave or convex. So the second derivative is really helpful to tell whether a section is concave or convex. If the second derivative is greater than naught, that means the gradient is increasing, So therefore that implies a convex section. It means it's slowing down, stopping, then going up. So therefore the gradient is starting to go up. If it was going down, it's starting to decrease because it's starting to increase in the opposite direction, and then it goes off. So that's a convex system. Whereas if it's negative, then the gradient is decreasing, therefore it's concave. So if the gradient is started by going up but then slows down and then starts to go down, that's where we get the concave sections. Just make sure you've got those in your notes. Second derivative positive means it's a convex system. Second derivative is negative, therefore it's a concave section. And you might be able to do some maths. If you've got the second derivative, you can show when that is positive and when that is negative, and therefore you can show whether you've got a convex or concave section. Okay, so when a curve changes from a convex section, so we can see that here, it's convex, second derivative is starting to slow down, now it's definitely going down. But at this point just here, what happens is the second derivative starts to increase. It starts to slow down that gradient and then starts to go up. Okay, so at that point just there, where it changes from a concave section to a convex section, is what we call a point of inflection. Now it could be the other way around, it could go from concave to convex or convex to concave, but the moment it changes is what we call a point of inflection. The other way of looking at it is if you look at the gradient function here, the gradient is clearly always on this side up here. If I draw my line, it's always on that side, but somewhere it changes. So here, if I draw my tangent line, it's clearly still on that side. But somewhere in here it changes because here, for example, now it's changed its side. We can see that the tangent line will be here on this side. So it changes from that side to that side. And the moment it changes is also what we call the point of inflection. Okay, it's when we change from a convex to a concave or concave to convex, but it's also where the flipping point is for the tangent line. So the tangent line was on here, now it's on here. Some point here, the point of inflection, is when that tangent line swaps from one side to the other. Now a point of inflection does imply that the second derivative equals naught. Okay, we can know that because on a concave section, we knew that the second derivative was negative. On a convex section, we knew that the second derivative was positive. So between those two, it has to equal naught. When it went from a negative to a positive, it must have equaled naught. And that, where it equals naught, is what we call a point of inflection. Need to be careful. Make sure you've got all these notes down. Pause if you need to, because you need to be careful, because it's not true the other way around. Having a second derivative equal naught does not necessarily mean a point of inflection. Okay, so a point of inflection implies that, but that doesn't imply that. And we'll look at an example of that now. Okay, so what I'd like to do, sketch a curve of the function x cubed minus 3x squared minus 16, show all the intercepts on the axes and the maximum and minimum points. So you've got lots of work to do there, so you might want to pause, take your time with it, draw a decent sketch showing all the intercepts of the axes and the maximum and minimum points. And when you're ready, you can carry on. Okay, so let's see how you got on. So if I've got that function there, I can definitely factorize it. I can pull out a 4 and I factorize it. 4 definitely is a solution, so therefore x minus 4 is a factor. And so I can plot that. So the intercept there is definitely going to be x equals 4. It doesn't cross again, but it does cross at minus 16. So I know that because it's cubic, it's going to come up. It could do that, it could come up and then do something here. Or more likely, it's going to come up here, do a turn, and then up like that. But what I do know is because this has no other real roots, then it is going to be turning somewhere in here. It could turn here, do that, but most likely it turns in this section. The way I'm going to do that is by investigating its maximum minimum points. So the stationary points are looking at the second derivative is 3x squared minus 6x. So that means that its stationary points are when it equals naught. So therefore 3x squared minus 6x. So I got x squared minus 2x, because I can just divide both sides by 3. And then finally, x and x minus 2. So it has some stationary points at both x equaling 0. So that's interesting. That means that that is probably going to be a maximum point or a minimum point as well. But also at 2. I can also, once I found those two, substitute them back into the original. Okay, back into the original to show that is a maximum point and that is a minimum point. So the graph's going to come up. It's going to hit there and turn on the axis. It's going to hit there and turn, and then it's going to go up like that. So now I can put my sketch in. Okay, so well done if you got that as your sketch of f of x equals 3x cubed minus, x cubed minus 3x squared minus 16. Okay, so what I want to do now is I want to just investigate some of the other graphs. So for example, what I'm going to look at is what the gradient function that looks like. Now we just differentiated it. We already know what the gradient function looks like because we just differentiated it and we saw that it was x minus 2. So that's why it's got those two values just there and there. It's a quadratic. It comes down because the original graph was x cubed. Okay, so that's what the gradient function would look like. But there's a couple of points that are interesting here. So notice that when the gradient graph is positive, okay, so when the gradient graph is positive, then f of x is going up. Okay, so just here, I look at this section just here, and notice that the gradient is positive. Do not look and think, well, the gradient is going down there. It's not correct to look at this as a gradient function just there. You're looking at when is this line greater than 0. So just here, for example, we can clearly see that it equals, there's a nice easy one, 10. It's definitely positive there, it's at 10. All of these values is positive. All of these values, the gradient function is positive. These values, though, are definitely negative. Okay, so when x equals minus 1, this has definitely got a positive value. So this is saying when the gradient graph is positive, in other words, from there to there, we can see that our original graph is increasing. Okay, and we said that earlier on. When the gradient is positive, the function is going up. It is an increasing function. Also here, when the gradient is positive on that graph, we can see that this graph here is increasing. It's positive. But also the opposite is true as well. If the gradient function is negative, like it is there, it's clearly below the y x equals, so the y equals 0 line. It's definitely negative. What does that mean then? This function is going down. All right, gradient at any of those values just there, if I drew my gradient line, I can see that it's going to be negative because the function is going downwards. It's almost starting to go up there and it's almost sort of tailing off down to there, but between those two values, it's clearly going down. So when a gradient is negative, a graph is decreasing, a graph is going down. And then the other points that is probably worth noting is that when the gradient is 0, there and there, is when you have a stationary point. So if you have the gradient graph, you know from the gradient graph when a graph is going up, when a graph is going down, and when a graph is turning, is stationary. Okay, so we've investigated what the gradient graph does in relation to the original function. Let's just do the same sort of thing, but with the second derivative. So the second derivative, there's my second derivative, 6x minus 6. What does that look like then when I plot it? It's going to look like that. So we've got the original graph, we've got the gradient function, and now we've got the second derivative on there as well. And just a couple of things that's worth noting with that second derivative. Now it's a straight line. You can see it's gone from cubic to quadratic to a linear function. Right. So when this is at this point just here, when it is negative, when it is below 0, look at what happens to the original graph. The original graph, that part is decreasing. Excuse me, not the original graph. The gradient function graph is decreasing up to that point. So you're doing the opposite to what you did before. When it's negative, the gradient function is decreasing, but the original graph is concave. Okay, so if you've got the second derivative, if it's negative, in other words, like it is here, look, negative, 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 there's minus 10. When the gradient, second derivative is negative, the first derivative is decreasing, and the original graph is going to be concave. And then the opposite is true when it's positive. So at this stage just here, for example, when x equals 2, y equals 6, so therefore it's definitely positive, 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 all these values. What happens to the gradient graph? Well, that is increasing. So the gradient is increasing at that point. And when you look at the original graph, then we can see that would be a convex system. So a convex system just there. But then also, just investigating the final point there that's important, is that when that gradient for a second derivative was 0, the gradient function was just changing from positive to negative, and this was a point of inflection. So that's what it's just saying there, those 2 points. Okay. Okay, so let's have a quick example then. So if I'm looking for the stationary points on the curve y equals x cubed, so you'd find the stationary points the same as what you do normally. So hopefully as soon as you see that, you're thinking, I know what to do. I need to find the gradient function, and then I need to set the gradient function equal to 0 because I'm looking for a stationary point. So let's just do that first of all. So if I differentiate it, I'm sure you've got 3x squared, okay, is my gradient function. I can then take that gradient function, I can find the stationary points because I know at the stationary point that dy over dx equals 0. So 0 equals 3x squared. So therefore x must equal 0. Right, now I can figure out what's the nature of this stationary point. So if I'm looking for what's the nature of the stationary point, then what I'm going to do is use the second derivative. So I've used this before to help me find the nature of the stationary point. What do? I'm looking for whether its maximum is, I'm looking for whether it's positive, negative, to help me determine whether it's a maximum point or a minimum point. The problem is when I look at the second derivative in this case, I get 6x, and when I put 0 into it, what I end up with is that the second derivative equals 0. Now the second derivative equals 0 is a bit of a pain. Okay, it doesn't mean it's a point of inflection, it means it could be any of the stationary points. It could be a stationary point of inflection, it could be a maximum point, or it could be a minimum point. So what I need to do is see how to figure out which one of those it is. But just be aware it's a very easy mistake to make, that thinking second derivative equals 0 implies it's a point of inflection. It doesn't. Point of inflection might imply that, but that does not imply point of inflection. Remember, it's a one-way street for that. So how do we determine what is this point just here, this stationary point? Is it a maximum? Is it a minimum? Is it a point of inflection? Okay, so grab your notebooks. Let's have a look and see how we go about figuring out if we get a second derivative equaling 0, whether that implies a stationary point, which is a maximum, stationary point, which is a minimum, or whether it's a stationary point of inflection. So these are the three situations. Either it could be a maximum, it could be a minimum, or it could be a stationary point of inflection. Notice that you've still got a gradient of 0 there at that point. All right, in the previous, what we said is if it's changing from concave to a convex, which it is doing here, that makes it a stationary point. You don't always get, it makes it a point of inflection. You don't always have stationary points of inflection. An example of that could be something like sine x. Okay, so the sine x function has lots of points of inflection, but they're not always the same as stationary points of inflection. Okay. Right, so let's have a look. How do we decide which of these stationary points it is? So the way we do it is by investigating either side of the second derivative. So we know where the second derivative is. Second derivative equals 0. So if we look at a value either side of that x value, so in the previous one we had x equals 0, so we could try x equals 0.1, x equals minus 0.1, and we substitute both of those into our second derivative. So we substitute in x equals 0.1, we substitute x equals minus 0.1 into our second derivative, we're going to get three different answers coming out. Either both of those answers are positive, both of those answers are negative, or there is a change between them. Now, if both of those answers come out to be negative, okay, so both of them come out to be negative, that's quite normal if it's something like x squared, right, minus x squared, excuse me. So we could see both of them coming out to be negative, therefore it is a maximum point. If they both come out to be positive though, so in this situation, you substitute in your 0.1, you substitute in your minus 0.1, and we see that both of them are positive, then we have a minimum point. And then finally, if we have a situation where on one side 0.1 gets you positive, but minus 0.1 gets you negative, then we have two different points, and that would imply a stationary point of inflection. The alternative to that is not using the second derivative. You might prefer to use the first derivative. And if we look at the first derivative, that could also tell us whether it's a maximum, minimum, or stationary point. Because if the gradient is going from positive to negative when you substitute in 0.1 minus 0.1 into the first derivative, if it goes from positive to negative, we know it's maximum. If it's going from a negative gradient to a positive gradient, we know it's a minimum point in between those. And if it's going from a positive to a positive, then in our first derivative, we know that it's a stationary point of inflection. So you can use dy over dx, or you can use the second derivative. Okay, some people think it just makes a bit more sense using the first derivative because they can get their head around whether it's increasing and decreasing. Totally your choice. Okay, so let's just have a look at this. So we've got y equals x cubed. We know that x was a stationary point. We just don't know when x equals 0 is a maximum, minimum, or stationary point of inflection. We don't know which one it is. That's not good enough on its own. So what we're going to do is we're going to check points either side of 0 because that was our x value. Okay, so if we check either side of our x value and we substitute it into our second derivative formula, so what do we end up with? Well, I'm going to use 0.01 and minus 0.01, 2 points very close to 0 but on different sides, and I substitute them in. So when x equals 0.01, I get a positive answer. It doesn't matter what value it is, I just notice it's positive. That's all that matters. Okay, so my next one, if that's also positive, then we know it's going to be, because they're both positive, it's going to be a maximum point. Or if it changes to a negative, then I know, in this case, it does change to a negative, so I know that it's going to be a stationary point, is a stationary point of inflection. Okay, so it's important to make sure that you can do that check and you can show that check. Even if you know what the stationary point is, the examiner is expecting you to be able to check it. An example of where you could have a stationary point that gets d squared y over dx squared equaling 0, but it's not a stationary point of inflection, would be something like x to the power 4. If you investigate x to the power 4, you would see where you get a second derivative equaling 0, but it actually ends up being a maximum or a minimum in that case. Right, lots of work to do because you didn't have any work on the previous differentiation section. So what I'd like you to do, please, is spend a fair bit of time practicing your differentiation skills, practice your understanding of these points of inflection and checking points of inflection. So have a go at those 3 exercises there then, please.